So it's a great pleasure to briefly introduce Eran Ofek. I'm sure most of you know him, and he specifically asked that the introduction will be very brief. Eran did his PhD in Tel Aviv, did his postdoc at Caltech, and arrived here at Weizmann in 2011. He won a long list of awards, and I will only mention the last two. So in 2015, he won the Krill Prize. This is a prize given by the Wolf Foundation to 10 young scientists in Israel across all disciplines in science. And in 2014, he won the Israel Physical Society Prize for an experimental researcher. He's the only one who won this prize. I should mention in context of outreach that in 1999, Eran co-founded the Tel Aviv Astronomical Club, which is a very active project that provides lectures to basically everyone, which is still active today, 16 years later. I had the opportunity recently to go there and join and also give a talk. It's still very active. I should say that if you want, Eran is what you would say is just a classical astronomer. If you open a dictionary and ask what is an astronomer, you should see a picture of Eran. Recently, I had to do some calculation that involved a little programming about movement of celestial bodies. I came to Eran. He said, yes, I have a program I wrote in the 10th grade that will answer your problem. I tried to put boundaries to what he's interested in. The only boundary I could find that he only does a little theory, but when it comes to observations, he covers practically the whole electromagnetic spectrum from radio, optical UV, X-rays, all the way to gamma rays. And in terms of systems, from the smallest bodies in the solar system through neutron stars to the most powerful explosions out there, which are gamma ray bursts. But today, he, among other things, will show us we need to go back to first grade and learn how to do addition and subtraction. Right? Thank you.
So let me start by presenting the people that are actually doing all this work that Boaz mentioned. Barak is mainly working on the algorithms, and you'll see some of his work toward the second half of this talk. Guy is working on subject that I will not cover today, but he has some contributions to speckle images, so that I will show something about it later on. And Nora Lynn Strojan was the PhD visiting student from Desi Zuten that works on precursors and IceCube. And during this talk, I'm going to cover two topics. The first is related to supernovae, and in particular, the recent discovery that some massive stars, just prior to their explosion, have some kind of eruptions in which they increase their luminosity and presumably also shed some mass. And this is likely related to the latest stages of stellar evolution. I will describe also the tools we are using to do all this. And this is closely related to another subject, which is how do we find these transients. And I will tell you about some challenges about how to find these transients, and in particular, a problem which is to subtract two images in order to find these transients. And the recent recent progress we have made on this topic with the help of Barak. Okay. So how do we do this? So the main tool we are using is the Palomar transient factory, at least our group. And the telescope is shown here. It's actually a very small telescope, only 1.2 meter in diameter. However, it's a very large corrected field of view. Part of it is shown here. This is a mosaic CCD called the PTF camera. For scale, you see the moon angular diameter on the sky. Typical telescopes have much smaller field of view than this, and actually it's smaller than the size of the moon. For example, this small blue box here is the field of view of the Hubble Space Telescope for comparison, which is 6,000 times smaller than this 7.3 square degrees field of view. So using this tool, we can actually cover a large fraction of the celestial sphere and image it again and again and look for transients, events that appear and disappear in the night sky. And here you can see a short movie demonstrating the operation of the telescope. And on the left side, you can see the sky coverage buildup since 2009 when we started this project. The color coding shows you the number of images per field. So
maybe it's better to switch the light on.
and it's the scale here is say 5,000 about. So in total, by the way, you can see this avoidance region is the Milky Way galactic plane, and at least in the beginning we avoided it. These regions are not visible from the Palomar Observatory. And in total, PTF observed, it's not moving.
That's nice. Just
In total PTF, the movie doesn't moving, but at the end you should see the entire sky actually observed. In total PTF observed over 2 million square degrees. And what we do with all these images? Well,
what is the technique of having that much larger?
Just large field of view, and many pixels in the camera. So what do we do with all these images? We look for transients. We look for events that appear and disappear in the night sky. And here you can see two examples, one and second. First, we have to prepare a reference image, which is just taking. We are just making it by coadding many images. And then we take a new image, subtract the reference from the new, and this is the residual. There is something here. It's here you can see a color image of the same sky location. This is an obvious transient. This is less obvious transient. And basically, this is the idea. The problem is that, as you'll see later on, this is actually not as easy as it seems. And there are many problems that related to this problem that I think that Barak actually solved a major part of this problem recently. OK, so until now, PTF found above 10,000 transients, of which we have spectroscopic confirmation and classification for about 2,500. And 90% of these transients are actually supernovae, exploding stars. And the supernovae comes in many flavors. The two most common flavors are the thermonuclear explosion of white dwarfs. These are the events that we use to measure cosmological distances. And the most common event is what we call core collapse of a massive star. These events are actually happening in the universe. Every 1 second there is a core collapse supernova in the universe. And just to remind you, during the life of a star, light nuclei are converted into heavy nuclei, and the binding energy is the gained binding energy is used to sustain the star against its own gravity. But when we reach an iron core, this process cannot longer take place because the binding energy per nuclei of iron peak elements is the highest in absolute value, I should say, in the universe. And this is why the core of the star collapses, and by some unknown process, or at least not well understood process, the envelope of the star is ejected. And in order to better understand this process, we really need to understand what the star is doing in the final stages of its life, and specifically what are the initial conditions of the supernova of the star prior to the supernova explosion. And this is one reason that it's not easy. It's very hard. Is that during the final stages of stellar evolution, some of the processes are taking place on dynamical timescale. And this requires hydrodynamic simulations in order to model, and this is at least not very easy to do. So just to remind you some basic evidence about supernovae. This is an example for a nearby supernova we found. And this is a typical light curve of a supernova, if I can use the word typical. There is some rise, which lasts for about a week or two. It's basically this rise time is in many cases governed by photon diffusion through the envelope. And since we know the opacity, we can actually get a rough estimate of this, the mass involved, which is a few solar masses. And this decay in many times is actually following an exponential decay with an exponential time scale corresponding to the radioactive nickel-56 decay into cobalt and iron. And if we take a spectrum, then we see these very broad features which have typical, which are broadened by Doppler, by the Doppler effect, and they have typical velocities of about 10,000 kilometers per second. Again, this is the velocity of the ejecta from the star. The typical energy budget for a core collapse supernovae is simply the binding energy of the star, and it's above 10 to the 53 ergs. Most of the energies come with, in terms of neutrinos, and about 1% is kinetic energy, and less than, usually 0.1% or so is actually due to radioactivity. And this is given the light of the supernova. This is the process that responsible in most of the cases, at least, to the fact that we actually see the supernovae. In some cases, so the reason you can actually convert this kinetic energy into luminosity on long time scales just by slowing down the ejecta and convert the kinetic energy into radiation. But in order to do this, we have to let the ejecta collide with some material around the supernova, which is equivalent to its own mass. And since the interstellar medium is usually very thin, it takes a lot of time to do this, and this gives us supernova remnants that actually seen for many, many years, actually 10,000 years after the supernova explosion, as conversion of the kinetic energy to radiation.
So why so much energy in the neutrinos? Why not gammas or something? You know?
So most of the I don't know to answer the question, but I can tell you what is actually happening is that in case of after the core collapse, a neutron star is formed. So this is and then you have some beta decays that generate the neutrinos, but this is not the only process. Then this proton neutron star is very, very hot, and the only cooling mechanism basically to cool it down quickly is due to neutrino emission.
There are gammas there, they cannot escape.
Okay,
but they can because
okay.
In the end, everything is
no. This is equilibration, but then it's hot thing.
Even the optical depth for
I understand that neutrinos can escape without equilibrating, but gammas equilibrate in the center.
No, but then you
equilibrate and then
lose all the
The what?
Gammas cannot escape and they lose all their energy.
Because there is an expansion.
Neutrinos escape in seconds. Gamma takes them.
and I will talk about this diffusion time scale soon, but it's actually I think that you have pair production in this case, and this is not okay. So what we really want to do is to study the initial conditions of supernovae before they explode, and one possible way is just to look for the star just prior to the explosion. So we need a time machine for that, or just simply, if we are lucky and we find a nearby supernovae like this one, and by chance the Hubble Space Telescope observes the same sky location prior to the supernova explosion, then we can look for the progenitor, the star that explodes just prior to the explosion. And this is what you see here. You can hardly see a faint point source, which is presumably the progenitor. We have to verify this by taking other additional images several years after the explosion. The problem is that this, of course, produces a very small sample. It's limited information, and it's biased toward the brightest or most luminous progenitors. However, there is some hope to learn more about supernova progenitor, and this is by a process called the shock breakout. And regardless of the type of the explosion we have, in early time after the explosion, we have a shock wave propagating through the star envelope. And this shock is mediated and dominated by photon energy. And this is possible because the density in the star is very high, and so the diffusion timescale, the time it takes the photon to randomly walk out of the star, is very long. It's actually longer than the hydrodynamical timescale on which the ejecta propagate. And therefore, the photons are trapped within the moving ejecta. But this, when the shock reaches lower density regions, eventually the diffusion timescale becomes shorter until the photons can actually stream out. And this is called shock breakout because the photons that actually held the shock no longer exist. And here you can see a schematic sketch, really a sketch that presents how we think it should look like. And start with the diffusion times, very short diffusion period. Then there is a flat part due to the fact that it's simply light crossing time effect. At early times here, we see light from the nearest point on the star, and later on we're starting to see the edges of the star farther away. This is simply the radius of the star divided by the speed of light. The total energy available here is roughly the energy, the thermal energy in the envelope of the star, which is proportional to the surface area of the star. It follows by shock cooling, and then the supernova kick in, whatever the energy resource is here. The reason I show you a sketch and not real observations, because it's not clear that we actually ever saw such an event. There is one candidate. And the reason it's so hard is that the timescales involved are very short. This is just for the largest stars, it will be about 1 hour. However, this is why we actually design in Ultrasat, which is a UV space telescope that is optimized to find these events. So what happens later? If there is a large amount of circumstellar matter, which we call CSM, above this shock breakout region, then this photon-dominated shock will be converted into a collisionless shock, and this produces hard X-rays and even GeV photons and TeV neutrinos. And recently we started actually to look for these signals. So are such supernovae exist in nature? The answer is yes. And one particular class of supernovae, which we call type 2N supernovae, which is a spectrum of which you can see here. For one example, this is flux, this is wavelength, and this time series of spectra. If you just look at the first one, you see this narrow emission lines featured on top of a blue continuum. By narrow, I mean that the Doppler width of these lines is narrower than the ejecta velocity. The typical velocity will be around anything between 10 to 2,000 kilometers per second, much lower than the ejecta velocity. And this is simply because the CSM is optically thick and it actually reprocess all the radiation beneath it. So one important question is how much mass is there in this CSM? The answer is vary dramatically from case to case, but I want to show you one example. And how do we do this? So it's very difficult to estimate this mass because there are too many details involved. However, if you do some simplifying assumptions, then you can get a rough order of magnitude estimates. Fortunately, we have several methods to do it, and the assumptions in these methods are somewhat independent, so we can actually have some balances and checks. And here is one example. So what you see here is the light curve of an extreme type 2N supernova. This is log luminosity, and this is log time. And the different symbols are for different wavelengths, but you should look at the black dots that actually represent the total light from the supernova. And if you just if you assume that this energy is coming from conversion of kinetic energy into radiation, then all you need to do is to equate the total radiated energy to the kinetic energy, and you can actually measure the velocity in some cases. So you can actually have a lower estimate on the mass of the CSM. It's a lower limit because if you don't assume anything about the efficiency, it's a lower limit. But we can do even better than that. There are some self-similar hydrodynamical solution for such ejecta moving into such CSM, and there are actually very solid prediction that the luminosity should evolve with t to the minus third, and this is exactly what we see here, this Paolo decay. And our interpretation of this break is that the ejecta accumulated mass, which is equivalent to its own, and these self-similar solutions are no longer correct in this regime, and it's become something else, which is actually momentum-driven. And but if this is true, there is one consistency check we can do. We expect that the total mass accumulated by the ejecta until this breakpoint will be roughly the mass of a massive star that is exploding, let's say 10 solar masses. And here is such an estimate. The blue contours show you the mass of the CSM mass estimated using this method. This is in solar masses. This is 11, 12, 13, etc. And this is shown as a function of two parameters, but these are the two parameters that the problem is most sensitive to, which is the shock breakout timescale, which is simply the diffusion timescale of photons, and the shock velocity during the breakout. And the red lines show you the observational constraints on the, and we also have some rough measurements of the velocity thanks to other X-ray observations using the NuSTAR X-ray satellite, which put the velocity at about 5,000 to 6,000 kilometers per second. This actually gives us a lower limit on the mass of the CSM accumulated up to this peak point, which is about above 10 solar masses, which is consistent with this idea. I should say that this is an extreme case, and in most cases the estimated masses are much lower than this. But still, the question is, what is the origin of this CSM, which is completely unknown, I would say. But there are some ideas. And just to give you an impression of what is involved, for example, there is some simulations that suggest that during the final stages of stellar evolution, oxygen shell burning in stars is fluctuating dramatically. The kinetic energy, the turbulent kinetic energy in this burning region is fluctuating very strongly. This leads to dramatic changes in the luminosity that can actually drive mass losses. And this entire argumentation actually gave us the idea that if there is a large CSM mass around this event, around this object, then maybe some of it was ejected in some kind of an eruption that was actually accompanied by higher luminosities. And this gave us the idea to look for precursors or outbursts prior to the supernova explosion. Before we started this, there was one case discovered in 2005, very weak transient, and 2 years later there was a supernova in the same location, yet another indication that something is going on. And so how do we find these so-called precursors? The idea is, first we have to find a supernova. Then we have to inspect images of the same sky location taken prior to the supernova explosion. We can do it better than that. We can actually coadd many, many images taken at the same location in some time bins and go deeper and therefore detect even fainter precursors. And this is the first event we found. This is the light curve of this event. This is log luminosity, log flux, and this is linear time. The supernova explosion is presumably here. And about 1 month prior to the explosion, these are upper limits, okay, no detection. And about 1 month prior to the detection, there is some brightening in the same location. Since then, we found at least 5 such events taking place between 1 month to 2 years prior to the supernova explosion. Again, we have no idea what is going on, but we suspect based on the temporal coincidence that it's actually related to the latest stages of stellar evolution. For type 2n supernovae, by the way, we found that, in fact, it's very likely that all type 2n supernovae have very bright precursors prior to the 2 years prior to the explosion of the star, and even that the rate of these precursors is even larger than 1 per year per event. So there are many, many such precursor events. We also found some possible correlations between the supernova luminosity and rise time and the total radiated energy of the precursor, which is actually makes sense if most of the light of these events are just the conversion of kinetic energy to radiation.
Is it known what the progenitor is?
So there is one. So type 2n's in general are probably a very heterogeneous group of supernovae. So there are many progenitors and probably also many mechanisms to derive this. But in some cases, we see what is called the luminous bright variables.
Because you said that most of them probably have precursors, but having a precursor truly depends on the type of star that
yes,
so you're saying many different stars produce.
Yes, so this is what we think, but I gave you the fact that I know of, which is likely all type 2n supernovae show these precursors. And in the cases we do know what a precursor is it's a luminous blue variable. That's it. And recently, we also found that these precursors are actually seen in other classes of supernovae, although they are much fainter and less common. So in order to do better than that, we need a bigger gun. And this is why we are building right now the Zwicky Transient Facility, which is, the idea is to use the same telescope as before, but having a much larger field of view. And this is the camera we are building, and it's actually under construction right now. 47 square degrees field of view. For comparison, the celestial sphere area is 40,000 square degrees. And this is the CAD model of the camera compared with the PTF field of view. This will allow us to find, this actually will allow us to find at least 14 times more transients per unit time than PTF. And we hope to use it especially for study early emission from supernovae and constructing large samples of precursors. And also, this actually using PTF and ZTF, we can actually go look for precursor 10 years or 1 decade before the supernova explosion, which is also very important. However, there are some problems. One of them is that the detection of transients itself is a very hard process, and because the image subtraction that I showed you earlier actually generates a lot of artifacts, and I will show you why soon. And in order to mitigate this problem, PTF relies on humans that scan the images and scan the candidates and select the best candidates before we actually do spectroscopic follow-up, etc. So, and right now with PTF, we require about 1 human at any given time. By humans here, I mean actually students, and it's not a very good use of our students' time. So, and the problem is, given the capabilities of ZTF, this is actually unscalable for ZTF. So we need basically better image processing tools. And there are many steps in order to find the transient in images. But let me tell you briefly about one important step in particular, which is probably the most critical in this chain of events. If you have a perfectly registered images, you want to subtract them in order to find the new transient in the images, and to subtract all the constant background and constant sky, up to the noise, of course. And this is the image subtraction step. I will just tell you that until right now, what we are doing is that after this image subtraction step, we are running machine learning algorithms which are not doing so well. And this is why, actually, after these machine learning algorithms are running, we still need this one human at any given time to actually scan the images. So why it is so hard? So the answer is, of course, the Earth's atmosphere. And some of my best friends really would like to get rid of it. And first, the transparency of the atmosphere is variable from night to night and actually all the time. And the background is variable. And this background of the night sky is actually the main source of noise in the images. Our basically images are what we call the background noise dominated. And most importantly is that the point spread function, or the way that the light from a point source is distributed, spatially distributed on the CCD, on the detector, is vary from night to night. And you can see an example for why it is here. You have a planar wavefronts coming through the atmosphere, through a turbulent atmosphere. Different patches in the atmosphere have a different refraction index. The result is that the wavefront is being distorted. And here you can see actually a realistic simulation of how this distortion should look like. This is above the aperture of the telescope. And when you image this to the focal plane of the telescope, you get this image, which is, you see several small dots here, right? If I go to logarithmic scale, you see that there are many, many spots. Each one of these spots is simply one diffraction limited image generated by these distorted waveforms in the focal plane. And there are many of them. And they are moving all the time because there is wind in the atmosphere. And the time scale for, for motion is about 20 milliseconds. This is actually changing all the time. And if you coadd many, many of these images, or simpler, if you just take long integration, you get what we call the scene limited image, just a very smeared star. And here you can see a short movie of how it looks like. This was were taken using the Krar Observatory on top of the accelerator tower. You can see the speckle images, the speckle dots, many of them, and here you can see how it moves. And if you let it average out, what you will get eventually is just a broad PSF. Normally, it can be approximated as a Gaussian. And this, the width, the typical width of this PSF is about 100 times bigger than the diffraction limit of the best telescope we have on Earth. So we're actually losing a lot of information, a lot of resolution due to the Earth's atmosphere. So let's talk about image subtraction. So in the literature, there are two types of solutions. The first is, and I will mention only one of them. The first is very simple. Let's go over it. So you have a new image, and you have a reference image, and you want to subtract them. Of course, you have to match the transparencies, etc. But let's forget about it because this is relatively simple. But in order to match the PSF, the light distribution, spatial light distribution on the detector, you have to do something to the images. And usually, the most popular solution in the literature is to convolve the image R with another image K, which we call convolution kernel, to make it similar to N in the least square sense. Okay? So, and this actually have a very simple solution, at least you may think so, which is just going to the Fourier plane, and this is the heads are here are Fourier transforms, and you can isolate K, and you solve the problem, right? However, this process, which is called the convolution, as you all know, it's numerically unstable, and you can see it very easily. If, for example, N and R both contain some PSF, and let's say that for simplicity, that this PSF is a Gaussian, the Fourier transform of a Gaussian is another Gaussian. So at the edges of this PSF, we have zeros or noise. And so at low frequencies in these images, we just divide noise by noise or zeros by zeros. And so we have nonsense. And when we go back to the real space, what we get correlated noise, or just noise everywhere. We just take power from some spatial frequencies to other spatial frequencies in the image, which is a very bad, bad thing. So the usual solution was to do what we called regularization, which is practically adding some additional information by restricting the PSF size, for example, to a finite size. Let this kernel be a set of basis functions. Use linear least squares to solve the problems with weight, so it's actually everything is more stable, and it actually works pretty well, and it's give much better results. However, there are still problems. First, you can actually show that it's the numerical instability problem is not gone completely. It's only it's still there, and actually in many cases it causes many subtraction artifacts in the images. There is no proof that this actually method is optimal in any way. You can see that it's actually not symmetric to exchange of R and N, which is a weird property. The final difference image is correlated because we convolved R with something. This means that the pixel noise is correlated. And in order to apply anything to the final image, we need to know the covariance between the pixels, which is usually unknown. And this just not good enough. More than that, you can see that if you look at the following equation, which is, let's convolve the n, the new image, with an arbitrary kernel kn, and convolve the reference image with an arbitrary kernel kr. This solution, for any n and r, have infinite number of solutions. Why? Because for any kn I will choose, I can find a kr that minimizes this equation in the least square sense. So this immediately tells us that we are missing a criterion here. And this criterion is actually very simple, which is it's equivalent to maximizing the signal to noise of a transient that appears in one of the images and not in the other. And the practical way to do it is to use the lemma of Neyman-Pearson. And just to remind you, who heard about the lemma of Neyman-Pearson? Nobody. Wow. Okay. Okay. So this 82 years lemma states that the most powerful,
Did you hear about it before you did this work?
Yes. So it states that the likelihood ratio test is the most powerful test for simple hypothesis testing. And let me explain what I just said. First, likelihood ratio test you all know, and the simplest example of likelihood ratio test is a delta chi-square test in the case of Gaussian distribution. Okay. By most powerful, I mean that the confidence interval on the answer is minimized. And by hypothesis testing, I will give you an example. Let's say I would like to find a transient in an image. So the first hypothesis is that there is a transient in a given pixel in the image with a given flux. This is an hypothesis. And I need to compare it to something else, which is the null hypothesis. There is no transient in this location in the image. So Neyman and Pearson actually gave us the method to do it, the likelihood ratio test. So you can actually apply this to this problem and find the optimal solution. This is optimal by construction. And this is what you will get. This is what Barak did, basically. And it's a weird-looking solution. But what I can tell you is that it has many good properties. First, it's optimal by construction. And second, it's numerically stable everywhere. And the reason is that whenever the denominator is approaching 0, the numerator approaching 0 even faster. So there are no division by 0 or any problems or numerical instability problems. And here is an example of how it works. And these are two images from PTF. You see that what we call the thing, the width of the star, is different from image to image. Here they are very big, here they are very narrow. And you can see that the images are not identical. There is some, you see these small streaks here and here. It's not appear here. It's, these are particle hits on the CCD detector, just what we usually call cosmic.
What is on the right and what is on the left?
Two images
of
the same field, and they are completely registered. Two images taken a different night of the same field. Thank you. And this is what you get when you do the subtraction. The only residuals are saturated stars here. And these small points are the very narrow points is actually the particle hits on the detector in one epoch and not in the other, I showed you earlier. And the noise is completely uncorrelated. This formula actually produces uncorrelated noise in the pixels, which is another very important property. So these are the advantages. Most of them I actually mentioned, but let me just say that it's also about an order of magnitude faster than the popular methods we are using for image subtraction. This means that actually it saves us a lot of computers, actually a lot of money, because the most intensive operations in finding transient is actually the image subtraction step. And it returns the probability that there is a transient in a given location. So it's no more machine learning and all this stuff. Okay. And until now I talk about image subtraction, but this can actually we can do this the same thing also for image coaddition, to coad in images. And I'll just show you the solution. This is again numerically stable. Whenever this approach 0, this approach 0 faster. The intuitive way to understand what is written here, P is the PSF, M is the measured image. The intuitive way to understand what is written here is that we given in the Fourier plane, in the Fourier space, each frequency we give it the best weight possible, which is the optimal weight for each frequency. This is what is written here. And the nice thing about it is actually it's condensed all the information from all the images we coadded into a single image without any loss of information. And there is only one important assumption, is that the dominant source of noise is the background and not the source itself. And let me show you one example of how it works. And on speckle images, you show how speckle images looks before. And these images were taken with the Carr telescope. There are 30,000 images. Each one of them is 7 millisecond exposure. If we just coad them by shift and add, just shift to the center of light and add, etc., then this is what we get. This is a little bit better than just let the detector integrate for 5 minutes. You see the star, and you see some smudge near the star. But if you apply this coaddition technique, you see the core of the star is much narrower now. It's actually diffraction limited. And you see the companion very easily. So we really hope that this method will have some, is important for improving eye contrast imaging, which is used mainly for binary star finding and planet findings. And let me summarize this talk by showing you the summary, and I can take questions now. Thank you very much.
Previous methods did an example of like that last picture to show what the previous methods of subtraction and addition, different methods. Like the right one is your method. Do you have any other method?
You ask if I have an example for other methods?
Yeah, an example.
No, not here. The answer is that, but I can actually describe it in words. In many cases, the results are good, but there is a slight loss of information, which is hard to notice. But in other cases, which are not negligible, there is a large number of subtraction artifacts that actually make it very difficult to find transient. But it is even more than that. Because the other methods are not well defined, they have a problem of defining what is a real transient and what is not a real transient. The bottom line is that they don't define correctly the probability that there is a transient in any location in the image. And this means that you don't have an honest way to tell if there is a new transient in an image or not. You have to rely on somewhat arbitrary criteria by, let's say, by increasing the signal-to-noise level to a level that you will trust, even without doing a subtraction.
So the certainty level is the most important advantage of the method, not the money, for example. Like from the list of advantages, your probability was missing in the
I tend to agree with this statement, yes.
Where were these images taken?
These images are from the Palomar Transient Factory in California, in Mount Palomar in California. This is the telescope I showed earlier.
And what do you have? The new camera you designed?
Sorry?
You designed a new camera for larger...
No, my personal contribution to the PTF project was that I made the robotization of the telescope. Mm-hmm. Just no human interference and so.
You showed
Yes.
resolution. And each one of these images is taken in a short time where the atmosphere is stationary.
Yes.
So it's important, but it's very faint. So
Yes.
is there an optimum to take maybe 1 million images which are even fainter, or each image has to be not so faint so you can do some reasonable calculation?
So this is an excellent point, and our method is much less sensitive to the. It actually works very well. Even in the example I showed, the number of photons in each image from the star is about 50. You can barely see it with your eye. It's like, and if you apply other methods, more sophisticated methods on these images, it just breaks. They don't work. You have to do something to the images. You have to restrict the size of the images to be very small. Otherwise, the noise from the background will dominate the cross correlation is done there. But
is there some intrinsic restriction on not having a large field of view telescope in space?
No.
Why do you need to fight the atmosphere? Just put this telescope in space?
money. So actually, NASA is now planning. There are two space telescopes that are space telescope with large field of view that are being constructed right now. One by the European called Euclid, and the other one by NASA, which doesn't have a name yet. And usually the technology that you send to space is 10 years older, so it's very hard to have the same sky coverage in space like you have from ground-based observatories. And these telescopes cost about $1 billion, while the price for PTF was about $3 million, and for ZTF is about $15 million.
So you said that you could prove that you have optimal distinction, but for a pixel, to decide whether this pixel has a transient or not. But the events you're actually looking for are not the size of a pixel, presumably.
Yes.
So if you have correlated events, does that change the method?
No. So it's a very subtle question. So you see that I wrote here that there are some other functions, and what is going on here is that in order to find a source in an image, it's not over yet. You need to apply. Effectively, what you want to do is to fit your PSF to this sky location and see what is the best fit of the flux, right? So you need the PSF of the image. And these methods come with expression for how the PSF looks like. It's another process of coaddition. And then what you do is basically match filtering. You just match filter your PSF with your image and find local maxima in the image, threshold them, and find transients. So I skipped some of the parts here.
The optimization is the same if you go through this step.
Yes.
It doesn't change.
So can you estimate by how much this will reduce the period of time that's needed to go over all these transients?
No, not yet. There are some things we don't know. For example, we don't know yet what fraction of the subtraction artifact is generated by each problem on the way there, because there are many steps on the way. For example, the registration step is also hard. We just need to do it more carefully. So I don't know, but the preliminary test suggests that it will be an important factor. I don't want to say anything more than that.
Okay, so let's thank Eran again.